Okay, so you see, right, for Cournot, so I followed the payoffs that you've given me. These are the rules that we have, right? So the thing about Cournot is that they choose the quantities independently of each other and simultaneously, right? And the total quantity is Q equals to Q1 plus Q2, and the price is given by the market demand, where we have the demand curve. The price equals to 9 minus Q, and then we know that for this case, we say that the marginal cost equals to 0. So we set up the payoff structure for both firm 1 and firm 2. So we can see that pi 1, which is the profit of firm 1, is nothing more than the total revenue of firm 1 minus the total cost of firm 1, right? And if we look at it, the total revenue is just price times quantity that firm 1 produces, and the cost, since marginal cost is 0, the cost is just 0. So this is our total revenue, and then this is our total cost, right? And then we get that it's just Q1 P big Q. And then we do the same thing for the payoffs, the profit of firm 2. You get total revenue of the second firm minus total cost of the second firm. And the same thing, you get price times quantity produced by the second firm minus total cost. And then you just get Q2 PQ. Okay, so that is like the base problem. And then you look at it, we have that the demand curve, PQ, is given by 9 minus big Q, right? And we know that big Q is nothing more, as we've defined here, as Q1 plus Q2. So we get 9 minus Q1 minus Q2. Okay, and then we substitute it back in to both of the payoffs. So we get that the profit of firm 1 is equals to Q1 P big Q, which is Q1 9 minus Q1 minus Q2, right? And then the profit for the second firm is Q2 PQ, which is Q2 multiplied by 9 minus Q1 minus Q2. So you see, remember, we set in the rules, right, that each firm independently and simultaneously chooses how much quantity to produce. So you see that for firm 1, it only can choose Q1. It only can choose Q1. So we treat Q2 as constant, right? Fixed. Because we don't know how much the other firm is producing. And also, how much we produce, we don't really need to think about how much the other firm is producing, because we can only control our Q1, right? Because it's simultaneous and independent. So the thing is, we don't know how much firm 2 is going to produce, but we want to find an expression to tell us how much we should produce for any amount of Q2 that firm 2 produces. And same thing, for firm 2, they can only choose Q2, right? So when we differentiate this function, okay, we take the first order condition for firm 1, we get 9 minus 2Q1 minus Q2 equals to 0, right? And then we take the first order condition for firm 2 as well. We get 9 minus Q1 minus 2Q2 equals to 0. So you see that in our first order conditions, for firm 1, we differentiate it with respect to Q1, and for firm 2, we differentiate it with respect to Q2, because firm 1 can only choose Q1, and firm 2 can only choose Q2, right? So we treat Q2 for firm 1 as a constant, and we treat Q1 for firm 2 as a constant, because we know that the other how much the other firm produces is going to impact how much we earn, but we don't actually know how much they're going to produce when we're choosing our quantity. So we just treat it as a fixed constant. So what this condition tells us, right, it gives us that actually if you check the second order condition, right, when we have delta square 1 over delta Q1 square, this is equals to you differentiate 9 with respect to Q1 is 0. You differentiate negative 2 Q1 with respect to Q1 is negative 2. You differentiate negative Q2 with respect to Q1 is 0. So you get negative Q2, which is less than 0. And you do the same thing on the other side. Like that. And you get negative 2, which is less than 0. So we know that in this, after we solve our first order conditions, this value of Q1 and this value of Q2 for both the firms respectively will give us the value of Q1 that will maximize our profit, right? How do we know that it's a maximized profit? Because the second derivative is less than 0. So this is a max. So the profit maximizing condition is for firm 1 is this, and the profit maximizing condition for firm 2 is this, right? So if we rearrange it, we have 9 minus 2Q1 minus Q2 equals to 0. And remember, firm 1 only chooses Q1, right? So we try and rearrange the equation to make it so that we have Q1 on one side by itself, and then we get that Q1 is equals to 9 minus Q2 over 2. And then we do the same thing for the firm 2. We get the same thing, which is Q2 equals to 9 minus Q1 over 2. Okay, so now what we've derived, right? You see, because we checked the second order condition, this value of Q1 maximizes profit for firm 1. And this value of Q2 maximizes profit for firm 2, right? But the only thing that we realize here is that because we know that Q1's profit depends on how much Q2 produces, and Q2's profit depends on how much Q1 produces, because the market price is a function of the total quantity produced, right? So this is what we call the best response function. The best response function for firm 1 as a function of Q2, right? And this is just 9 minus Q2 over 2. So this expression tells us for any value of Q2, what is the corresponding best value of Q1 to maximize our profit. Okay, so far? And the same thing, we get that the best response for firm 2 as a function of Q1 is nothing more than 9 minus Q1 over 2. Okay, so let's say we sketch the graph now. We have a graph like this, where we have Q1 here and Q2 here. So for firm 1, okay, maybe I'll do firm 2. Firm 2 we get 9, so we know that it's Q2 equals to 9 minus Q1 over 2, which is 4.5 minus half Q1, right? So we just draw a line, intercept 4.5 with a gradient of negative half, and we label this curve the best response function of 2 given Q1, where, I mean, if we want to label it, this would be 4.5, and this would be Q1 equals to 0, Q2 equals 4.5, Q2 equals to 0, Q1 equals to 9, right? And then we draw the same thing for firm 1, and then we get that this is 4.5, and this is 9, because Q1 equals to 9 minus Q1 equals to 9 minus Q2 over 2, which is equals to 4.5 minus half Q2. So actually, if you look at it, if you look at both of these best response curves, they're actually just like a mirror image of each other, kind of. That's why we say that their payouts are symmetric. So we call this the best response function of firm 1 given any Q2. So how we interpret this graph, right, is you remember something really important is that firm 1 only chooses Q1 and firm 2 only chooses Q2, right? So let's say we look at the best response function of firm 2, right? If Q1 is chosen to be this point, then the best response for player 2 would be this point. So let's say this is Q1, then the best response would be Q2 star, right? Q1 star, Q2 star. Agreed? And then similarly, for firm 1, if let's say Q2 is chosen at a point maybe here, where this is Q1 hat, then, sorry, this Q2 hat, then firm 1 wants to produce Q1 hat, right? Because the best response function tells us that if firm 2 chooses Q2 hat, the best Q1 for me to choose would be Q1 hat. So how do we use this diagram to get our Nash equilibrium? If let's say I redraw the diagram neater again, I get Q2, Q1, like this, 9. Okay, maybe not. Yeah. 9. This will be 4.5. This will be 9. Okay, so we look at this problem, right, and we analyze the best responses. So let's say I start with any arbitrary value, okay? Let's say if firm 1 chooses Q1 equals to this point over here, right? What would firm 2 want to produce? Firm 2 would want to produce this value, right? So let's say this point is Q1 prime, and this point is Q2 prime, right? And let's say, but if firm 2 produces at Q2 prime, what does firm 1 want to produce? Firm 1 would instead want to produce at this point, Q1 hat. Okay, but if firm 1 produces at Q1 hat, what does firm 2 want to produce? Firm 2 wants to produce this point, which we'll call Q2 hat. So you see, right, the problem with picking any arbitrary set of values is that both players, if I know that firm 1's playing Q1 prime, I want to play Q2 prime for firm 2. But if firm 1 knows that firm 2 is going to play Q2 prime, firm 1 instead wants to play Q1 hat. But if firm 2 knows that firm 1 wants to play Q1 hat, firm 2 wants to play Q2 hat. So you see that, and you can test that for any arbitrary point, because the idea is that these points are all not Nash equilibrium, right? And there's only one point where both of them intersect, which is Q1, Q2, 9, 4.5. Okay, which is this particular point over here where they intersect, right? If firm 1 chooses Q1 star, firm 2 wants to produce Q2 star. But if firm 2 is producing Q2 star, we dot back to the curve, the best response curve for firm 1 still wants to produce Q1 star. So you see that at this particular point where both of the best response functions intersect, it tells us that both players, or both firms rather, are playing best responses in response to the other firm's strategy, right? So that's all that the diagram tells us. It tells us this BR1 is a function of Q2, tells us firm 1's best responses for all values of Q2, and this best response function 2 as a function of Q1 tells us firm 2's best responses, their best choices of Q2, given any Q1. So why do we need to draw a diagram like this? Is because you need to remember that at the start, we said that each firm is producing independently and simultaneously, which means that when they're making their decision on how much to sell, firm 1 doesn't actually know how much firm 2 is going to sell, and firm 2 doesn't actually know how much firm 1 is going to sell, right? So if firm 1 chooses to produce maybe at this point, and then we know that firm 2 wants to produce here, but firm 2 produces here, firm 1 wants to produce here. So you see how these are all just this is how we use the best response function to aid in our analysis. And so that's really what the diagram just illustrates to us why this is a Nash equilibrium, because at the point where they intersect, neither of the firms want to change their quantity, because that is in some way kind of their best. Both of them are already playing best responses to each other. So if we look back at it, we have that the best response, we have, let me copy it down here. For firm 1, let's say I say now, instead of, I just now I wrote Q1 equals to 9 minus Q2 over 2. And then the best response function of 1 as a function of Q2 is 9 minus Q2 over 2, right? And for firm 2, so now we develop the analytical solution for it. For firm 2, we know that Q2 is equals to, the best response of Q2 is 9 minus Q1 over 2. And so we say that the best response function of 2 given Q1 is 9 minus Q1 over 2. And by definition, we know that the Nash equilibrium can only exist when both players are playing their best response. Yeah? So let's say we don't know what exactly this value is, and that's what we're trying to find, right? So let's say I say that in Nash equilibrium, both players are playing Q1 star and Q2 star respectively, right? So now we have two equations. We have Q1 equals to 9 minus Q2 over 2, and Q2 equals to 9 minus Q1 over 2, right? And let's say we assume that there is some Nash equilibrium where both of them are playing their best response strategies, it means that these two equations, Q1 star, the Nash equilibrium quantity that firm 1 produces, will be equal to 9 minus Q2 star over 2, right? Because in Nash equilibrium, both of them have to be playing their optimum strategy. So there's a star here to tell us that these are the best quantities they can choose, right? And similarly, we have that Q2 star is equals to 9 minus Q1 star over 2. So now, for Nash equilibrium to exist, both of these equations must hold, right? So we solve them normally like simultaneous equations. I put 1 and 2.